Good afternoon and welcome to the LCANZ Autumn Webinar Series and our third in the Carbon series. Great to have you all with us today. I'm Emily Townsend, I'm President of LCANZ and I will be your host for today. Thank you all for joining us. We'll be getting started properly in just a moment, but just a reminder if you haven't already, that we have 3 more webinars following this one. That will be our water series. We are going to be taking a break over Easter and the school holidays, so they're starting from the first week of May. So if you haven't, please go to the website and register so that you don't miss out, because while carbon is the now topic, water is most definitely the next, and the next thing that we all need to be preparing for. Also a reminder that we are running a competition, so there's a free LCANZ membership up for grabs, either your own membership if you're a student or individual, or if you're a corporate member, you could win a free membership to pass on to one of your suppliers, one of your SMEs, to help to grow the LCANZ community. To be in with a chance to win, you do need to register for the webinars and attend them, and there will be a short quiz that will cover the content across all of the webinars that we've gone through, so pay attention. I would like to acknowledge and thank ThinkStep, as we are using their Zoom account, and also to thank our LCANZ members, because without them, the webinar series would not be possible. It's paid for by our membership subscriptions. So those of you who are not yet members, please do consider becoming one. We are very reasonably priced, and new members joining now will be covered through the FY23 membership cycle to the end of May next year. And obviously, if you win your membership, we can pay you back. So don't let that put you off. So on to today, I'm delighted to welcome Dean Cook, our speaker. He is the Divisional Technical Manager for the Concrete Division of Fletcher Building and was instrumental in development of Firth's EPD and carbon calculator for concrete. And it's the carbon calculator that he will be talking to you about. So Dean, over to you.
Today, we're talking about low carbon concrete. Very quickly about Firth. Firth runs concrete ready-mix plants, masonry businesses, and bagged dry-con products. We're sort of the largest in each of the sectors. Therefore, we have a sort of an industry responsibility to lead the industry, and we take that very seriously. As you're all aware, when we're doing our life cycle assessments, that the A1 to A3 section is usually where a material EPD, and when I talk about our calculator and talk about our EPD, it is a cradle to the gate leaving our plant. What I'm finding interesting, though, is this is just a slide, as we all do, stolen off the internet. I'm seeing that the definition of changing slightly, where embodied carbon is meant to mean both the construction phase and the operation, excluding the energy component of it. So I'm hearing this A1 to A5, the red box being described as upfront, and embodied in everything minus the operational energy use. So that's an interesting slight change I'm seeing. So Firth worked with ThinkStep and Start to See to develop our EPD. And here is an example. It's live on the internet, public domain. You can download it. Gives you our EPD information for all our plants. This is an example for 20 MPa of all the North Island plants. There's another one for the South Island plant. When we did this, though, these are a summary of what you used to be in history. So it's FY19. We needed more than this. So when we talked to work with ThinkStep, what we asked them to do is also work with a calculator. Now, part of our other EPDs that inform our calculator are the Golden Bay EPD, which is public domain as well, and Wisdome's Aggregates, who supply a lot of our aggregates. They have only just released them. It's sort of hot off the press, their EPD. And in each cases, these are sort of, I'd say, best of class in terms of their environmental performance. Before we move on to the calculator, if you're doing life cycle assessments, when you're starting to look at the B1 section, you'll find that you can consider what's called carbonization. So concrete reabsorbs CO2 with time. If you go to EN 16757, there's lovely equations that you can use. Being an engineer, I love equations, but it is relatively significant. Per square meter, you would get about 5 kgs absorbed over 90 years, which when you start multiplying by large numbers of square meters becomes significant. And it can be about 15% of the CO2 in the concrete's reabsorbed. Interesting enough, when people start talking about road maps and footprints, they often look at all the concrete that was existing. And this outfit in Europe that has been working with the IPCC, for New Zealand, it would be of the order of about 70,000 to 130,000 tons of CO2 was sequestered each year by all the concrete that we've poured before. Not really an LCA issue, but interestingly, but an LCA issue can be the end of use. If you take concrete, crush it right up, it will have never done its complete absorption that it's able to do. And there's a potential of about another 60 kgs per cubic meter if you have some sort of end of life processing. And a lot of work's being done in this area, and you know, that's probably about 30% of the original footprint. So onto the topic, carbon calculator. As I say, what we found was we did our EPD, but we didn't want something that just sat on the shelf. What we wanted is something that was live. We have really experienced and skilled engineers that are very skilled at making sure that you get the lowest cost and the performance you required. With this calculator, it allows them also to be able to look at the carbon footprint as a decision-making thing. And what it does is we can select the plant. We've got, as I say, 72 odd plants around the place, put in a mixed design, and it will, and the ingredients, and look at using supplementary cementitious, different sources of cement, different sources of aggregates, and it will come out with our carbon footprint. It allows our engineers to work now on strength, cost, and carbon performance, making rational decisions there. Because with concrete, you'll often find that there's a specific need, and therefore you tailor it for that need. So this starts to allow us to look forward rather than back. And with it, we were able to present a certificate. It's in the form of an EPD, but obviously it's not quite an EPD because it's something you're about to produce. But that will pull through the certificate, the name of the concrete, and it will provide you with all those environmental impacts that you would see in an EPD. And then because we find that most people are not that keen on numbers, we started to develop a little rating system. And with this one, because it's 25% lower than the baseline, and I'll explain the baseline later, we call it an EC20. So anything that's 20 and above gets rated as EC20, so that people can specify concrete rather easy. I want a 30 MPa EC20 mix, and that means something to everybody. I'll go into a little bit more detail in the next couple of slides. How can this impact? Here's an example of a job we recently did. It's had 4,500 cubic meters. We developed a mix in consultation with the team that was about 28% better than the baseline. And so there's almost 500 tons of CO2 was saved through that process of sort of consultation, coming up with the correct mix. So what is this EC rating? All we've simply done is we've taken the various strength grades, and with concrete, the higher the strength, the more cement you need to put into it to give you that strength. Therefore, the higher the footprint. We picked a baseline, and at the time, NZTA were doing a lot of work with the Infrastructure Sustainability Council. It was of Australasia at that time. We picked their 2020 baseline, put in the strength, that gave us a baseline. And then we simply said EC10 is 10% better than that, EC20 is 20% better than that. So that means that if you wanted to order 30 MPa concrete that was an EC20, then our challenge would be to make sure that it was at least 30 MPa strength, and the carbon footprint as calculated using our calculator was less than, in this case, 278. And there's what that means is it becomes performance based. It's not people saying put in this material or doing something like that. You're setting a performance criteria, and then we find the best and most sensible way of achieving that challenge. So how do we achieve that? Concrete is basically cement, coarse aggregates, sand, water, and some admixtures. And it's these two that are ringed as green, where we have the levers to do some work. Although this only represents, the cement represents about 8% of the concrete by volume, it's about 80% of our footprint. So a lot of it is focused on reducing the cement content. First thing you do is you find the best cement you can, and Golden Bay is the sole New Zealand manufacturer, and we should be proud of their footprint. They've done a lot of work over the years. Their global warming potential, and the difficulty for people comparing cements is they're not all the same strength. So I would describe Golden Bay cement as a full strength or high strength cement, which means I don't have to put much in my concrete to make my concrete strength. And it's got a global warming footprint of 732, and this number is going down. They've done a lot of, this is historic again, done a lot of work on alternative fuels. They've done a lot of work using close to half, I think, of New Zealand's tires shredded and put through the plant. Doesn't do much for the carbon footprint, but does a lot for you if you've got a mountain of waste tires next door to you. But this number is going to be much lower than 732. Comparison, the imported cement, and this is really good cement. This comes out of Japan, high quality plant, 897. That just shows you how good this number is. So first strategy is get really good cement. Second strategy is to look at supplementary cementitious materials. We can use fly ash, we can use silica fume, we can use some natural pozzolans, and we can use something called ground granulated glass slag. There are others. They come with pluses and minuses. The advantages of that EC rating type process I was talking about is it becomes the concrete supplier's responsibility to find out which one of these are. But each one of these has the ability to reduce your cement needs and therefore reduce your carbon footprint. And the calculator we've got can take those into account. Where's the world going? And in New Zealand, we're looking at our roadmap, but this is one for the Global Cement and Concrete Association. And people are looking at how I change my clinker to reduce the amount of clinker that I have in cement. How do I get more efficiency in concrete production? Not a big issue for us, decarbonisation of electricity. Carbon sink, I've done calculations and I suspect our carbon sink of existing concrete is around about 9%. Using supplementary cementitious materials will be bigger for us. Recarbonisation, carbon capture and utilisation, this big chunk here, is something that a lot of the industry's looking at the moment. And I'm hoping that in sort of the next 10 years or so, that starts to become less prototype and more full on. And there's the design industry looking at various ways of improving our standards, etc., to remove conservatism and get efficiencies that way. So you can see that there's a big picture in how to achieve it. And that big picture involves lots of different sectors and everybody sort of doing their little bit.
Thank you. That was incredibly informative and interesting. And yes, you kept well done. So yeah, thank you. A couple of thoughts before I start going through questions that people have sent in, but I'm taking prerogative as host. Really good point about how embodied carbon is now really being considered to not just be the upfront emissions in the materials. And you probably know this, but more for those who are on the call, it's to do with the fact that when you specify that material, you need to account for the fact that whatever then happens to it during life, whatever it needs during its life, is built in at the start. So if we specify concrete, whatever it needs during its life you kind of have to account for at the point you put it in. It's not just going to vanish. So yes, there's a lot of different terms that are coming up, but certainly the upfront for A1 to A5 I know is favoured by NZGBC as well. And yeah, useful to understand. I love the concept of specifying by carbon reduction. That just makes it so easy. And my first question is, what's the reaction from specifiers and from customers? How's that landed?
No, really good, because what we've done also is people say, oh, how do I specify? So what we've done is we've done things like gone on to master spec, which is a sort of resource for designers, and written specifications there that says this is how you do it. And what I quite like, because as I talked at the beginning about Firth being the largest and therefore has some responsibilities around leadership, is by we live in a very competitive industry. So if you just say, here's the targets, everybody go out and find the best way of doing it. One, we're really interested in transparency upfront, so that you can see it and make the challenges real. So we've had a lot of people asking us about it, what we can do. At the moment it's slightly embarrassing in that with the way the world is with COVID at the moment, it's very difficult to bring anything in from overseas. So the number of levers we can pull is limited, and also you just wish you could go faster. But every time you do something, it's a 6-month to 12-month cycle, and then you say, woohoo, there's 5%, I've done it. It's very easy to write it, it's very difficult to do it, but lots of enthusiasm. And I think we've tried to keep it nice and simple. And what I'm finding when I talk to people is they find it very easy to say, I want an EC30. And it is totally coincidental, but at Firth, we reckon nearly most of our concretes are hitting around about EC20 right now. So we sort of said, oh, EC20 in 2020. Well, let's target EC30 in 2030. Well, I think we're going to be EC30 if things go the way we would like them to go, if researchy things, then maybe in a couple of years' time, we will have already achieved that. In which case, you say, right, now we're heading for 40. And the nice thing for us is that when people write benchmarks and then you get to it and everybody's happy, and then all they do is change the benchmark, sort of slightly, you feel like you haven't achieved anything. But at least this way, we can see ourselves coming down all the time.
Yeah, I agree, absolutely. And I think it's a great way to specify, to be able to leave the technical details of how you do it to you or to any other concrete manufacturer, and just say, well, this is what we want to achieve for our project. How do you help us? We
found that people struggled if you said, oh, concrete is this number if it's 20 MPa, this number if it's 30 MPa. It's just like overwhelming numbers. But keeping it as something which has an inherent meaning, not difficult. Yeah,
makes a lot of sense. Awesome. So I'm going to go on to the first of the questions that's come in, and actually feeds off of this bit. Firstly, Ruhola, I hope I pronounced that right. Sorry if I haven't. Thanks you for the informative presentation. And would you advise on the types of tests needed to be done for the durability of the low carbon concrete to be accepted for construction?
Okay. I suppose what I will say is that every piece of concrete that we sell with EC rating, will be absolutely compliant with the standard. So there'll be no reduction in strength, there'll be no reduction in durability. We wouldn't put it on the market if that was the case. The reality is that with all these options, you invariably improve the durability, because you start to use supplementary cementitious materials. They tend to fill up all the little pores, they tend to be more durable. We've traditionally used fly ash, microsilica, slag, as a niche product for high-end durability, acid resistance, chloride resistance. So the beauty of the simple system we've developed is compliance with the building code is still governed by all the standards. So these mixes have to comply with the standards. That's the bottom line.
Yeah, which again makes it easy for specifiers, because they're not.
Yeah,
they're just Yeah, awesome. Thank you. Another question from Lindsay. The golden-based cement that's at 732 kilograms CO2e.
Yeah.
What per cubic meter? And I think I know the answer is going to be it depends.
Yeah, well, because that's why we say that EC rating for the concrete, because even if I was to if you were to go to our EPD and look at a 20 MPa concrete, they could have anything from 200 to 280 kgs of cement depending on their aggregates, because the beauty of concrete is that you use your local resources. So if you've got really good aggregate, I live down in Christchurch, we often refer to Paradise, and we've got really good aggregates. We can make really good concrete with very little cement. You go other places, they haven't got that luxury, but you don't want to cart aggregates on way. So the number varies, and that's the beauty of the calculator. The calculator sits down there and says, at this plant, these are the logistics of getting my cement here. These are the logistics of getting my aggregates here, all the admixtures, everything to it, and therefore it's a single number at that plant. And then we can start to say, right, and now what can we do at this plant, which is your closest plant? What can we do to improve that? Can we look at using, there might be, will we look at using admixtures? Is that the best option? And the thing I say is always have a conversation, because concrete, a lot of concrete is not just the strength, it's about being able to place it, get it in place. You don't end up with big air holes. It doesn't delaminate. You don't have those sort of problems, because there's no carbon saving in the concrete you put down and then you take out again because it cracked all the way through. So, there are some times when you can use really specialist mixes and they will work. And there are other times where you say, look, this is just too much of a risk. Pull back on the aspirations and let's do it once. So, that's why we say, look, we're not scary people. Come and have a chat to us. All our contractors will. So it's about setting sensible challenges, and year on year, what's sensible will hopefully come down.
Yeah, absolutely. That's
really our big dream in our industry would be to have a really good carbon capture system, which as I say is there's prototypes. It's not there yet. But if we could get to the stage where everything that was cement was captured and utilized in a product, concrete would be carbon negative, because you would say it then goes out and starts soaking up CO2 while it's sitting there. That would be a dream to be in there. There's a lot of work to go before you get to there, but that's the aspiration.
There isn't there, yeah, and it's a challenge, and for those who are not familiar with the cement production process, a huge amount of those emissions are from process emissions, right?
Because you take limestone and you really heat it up, and that drives off CO2, and so that's the part you want to capture. You can do all sorts of engineering to engineer out all the other components, but that's a chemistry one. So that's what you want to get your carbon capture, and if you capture that and utilize it in some way, life is good.
And that's where I think carbon capture will be so important, because it doesn't matter how many fossil fuels you take out of the system, there's still that bit that you can't deal with in any other way. Sure. Yeah,
it's a chemistry part.
It is. Wonderful. Question on carbonation, in fact, again from Lindsay. He's got all the questions. He's interested in the figures you gave, as his investigation suggests that 3% is good even for optimum applications like concrete roading. And what can we realistically expect in buildings?
All I did was run through the calculations. I worked on about 5 kgs a square meter. There's lots of variables on it, and it's got a lovely little equation, but it depends on whether there's an optimum moisture, which the way carbonation works is you've got calcium hydroxide in the concrete, CO2 comes in, they react limestone, and for that reaction there's a peak there's temperatures plays a role, moisture content plays a role. When you look at those equations, it says if you're inside, you're outside, because that's wet or dry, those sort of things. And I suppose it's a surface area. So that's why I put it as kgs per square meter. So if you've got a thick, a concrete road will be 200, 250. You're still getting 5 kgs a square meter, and it's a fair volume. If it's 100 mil thick, that's why concrete pavers, 50 mil thick and quite porous, probably carbonate a lot more than anything else. And some work we need to do there, because I suspect as per hardscaping, the concrete paver is actually quite a good solution.
Yeah, that makes sense.
But so I work on per square meter rather than a percentage.
Yeah, that makes a lot of sense.
What I should point out there is that it is a surface related, and it's relatively modest. The interesting thing is the ability at the end of life, if you crush it up create a whole lot of extra surface area, there's a lot of potential to soak up some additional CO2.
Yeah.
And that's where I'm seeing a lot of technology around, and it's aggregates type people that will come in, they crush the material up, put it in a container, it's got elevated pressure, elevated CO2, and it soaks up.
To make it soak it up more quickly.
Yeah.
Yeah,
exactly. And there's work being done in that area. So there's some good ways of reducing it at the end of life.
Yeah. Awesome.
Interesting though, sorry to keep you when you sort of say you've only got, it's modest, we're getting this 5 kgs over 90 years, but when you start to look at the whole of New Zealand and say how much concrete that's sitting there, it adds up to 70 to 130,000 tons of CO2. Big numbers, because we've poured a lot of concrete over the years.
We have, and we will continue to. And sorry, while we're on that, Stuart's just asked to please repeat the mechanism for absorption. Okay. You were so quick that he missed it.
Right, sorry. So within concrete, you when you pour concrete, floating within it is a lot of calcium hydroxide. Okay. Now, if you go and have a look at a wall and there's been water coming through it, and you get a white powdery on it, that is calcium hydroxide coming to the surface. And then when it gets to the surface, it reacts with the CO2, and you get that white powder, which is called efflorescence, which is basically limestone, calcium carbonate. That can happen within the body of the concrete. So if you get CO2, the first thing it tends to do is go looking for the calcium hydroxide and convert to limestone. But it's a self-blocking mechanism, because the CO2 gets in and then creates this limestone and blocks it. So it gets slower and slower with time. That's the sort of process with really extended carbonization. You can actually start to break down the calcium silicate hydrates, but that's really impractical. And it is limited. It's 20 millimeters of the surface, you know?
Yeah.
So, yeah. But there's lots of people have done work. And as I say, people have done the equations to say, right, this is a verified method you can use. You just have to pick whether you're inside, outside, wet, dry. Yeah. Those are the key ones.
Makes sense. I take it we don't need to worry about any less loss of strength as it's turning into limestone.
No, it's nothing to do. It doesn't affect the strength, because the calcium hydrides are still there. You're actually putting little bits of limestone in the little holes. What I would say though is it usually reduces down the pH. So that's why we have cover in reinforcing. And because as soon as the pH drops to 10, 11, then there's a potential for reinforcing to corrode. And that's why we have those covers, because that influence is going to take it 90 to 100 years to get it to the start, you know, and then you've got to go beyond there. And that's why it's a surface related issue.
So very important to design it properly and lay it properly.
Well, if you comply, New Zealand standards tell you what cover you need to do. If you follow those, you've got well over 100 years life out of it.
Is the electrolytic process of producing Portland cement under development by MIT on the radar for the New Zealand production market? The process would reduce the need for carbon capture. That made sense to you?
No. Well, it did. It did, but I don't know the answer.
Fair enough.
Because there's so much different technology out there, different types of cements, different processes that are sometimes not quite sure which one is which. But there's been lots of work. There's different types. There's people looking at different cements. There's people looking at CO2 being used as the curing process. There's a whole lot of innovation in there. And some of that work will go from lab to prototype to full scale. Some will die somewhere along on that chain. But I'm not sure what the actual question was, but I can assure you that we are looking at everything every day.
Yes, yeah, sure. Wonderful. And last one then. So again from Lindsay, is there much discussion in the concrete sector as to targeting good deconstruction and pointing out that we need to consider the end of life issues at the beginning?
Yeah. No, we've been, there was probably 15 years ago, I can remember doing a lot of work with what they used to call the press technology, which is a lot of precast type technology that was designed using unbonded tendons, so that you could actually, at the end of life, take it all apart and you could actually build it somewhere else if you wanted to. The airport, Auckland Airport, was built using that technology as a temporary structure that is still there today. So yeah, there's been a lot of work done on that, and a lot of work done also from seismic engineers looking at low damage design so that it survives earthquakes without the need to rebuild, because it's deformed and then there's virtually no damage. So all those things are on the radar.
Yeah, no, that's a good point. And I think concrete buildings are typically so long lived that it's more important to have the shell and then being able to redesign the interiors, so do fit outs that meet new things over time, which I think is pretty much the norm now, is that it tends to be the shell and everything within can be changed.
Yeah.
Wonderful. Dean, thank you so much. That was fascinating. And as you can tell by all the questions, it's obviously been a very interesting webinar. I can see a few thank yous as well coming through. So thank you very much for your time. Just to say thank you, everybody, for attending. And not to forget, as I mentioned at the start, we do have some more webinars coming up in May. So hope to see you there. In the meantime, have a wonderful Easter break. Don't forget our competition, and that you will be able to go back and rewatch webinars if you have forgotten anything. And please do consider joining us if you're not already members. Thank you very much and have a wonderful Easter. Thank you, Dean.
Bye.